Hey, hi guys, good morning.
Good morning.
All right. So, any questions? All right. So, yesterday we discussed about this two sample test um, where we have covered one scenario where, yeah, 1 second, where we were comparing the two independent samples. Okay. And we will see that how we can compare the two independent samples. So when we are saying two independent samples, means those two samples have been drawn from two different populations. And here the idea is, to compare the two populations and infer that whether those two populations are same or they are not same. Okay, that is the major objective of this particular two sample test. So definitely we cannot compare two population because we do not have the data and that is not feasible. So what we do is we derive the samples independently from these two populations, and then we measure based on those two samples. Either it could be mean or it could be proportion. So currently we are discussing about mean test. So here we will see that how by calculating the mean from each of those two samples, we go and do some kind of hypothesis testing on top of it to infer about the population. So again, when we talk about independent samples, uh, again we get two different kind of scenarios. One scenario is where we will have information about the population variances, and another is where we do not have any information about the population variance. So now we will again go through this particular scenario where we will have an idea about the population variances. If the population variances are given to us, then we go with the Z distribution. Okay, that is kind of standard. Even if in one sample, if we have some understanding about the population variance, there also we have seen that we are going with a Z distribution. Okay, so yesterday we have seen that in this particular scenario where the population variances are known, then we go and calculate this particular thing is called as pooled variance. Pooled variance is a variance which we are calculating based on the individual variances of the population. So here the pooled variance is calculated by sigma 1 square by n1. This is the sample size plus sigma 2 whole square by the sample size of sample 2. Okay. Once we get the pooled variance, then we substitute that into this particular equation where we'll take the difference of the two population sample means. This, as I mentioned yesterday, this you can ignore. Just take the difference of the two sample means divided by the pooled standard deviation. So this is pool variance. We take the square root of this pool variance. Now this will become a standard deviation of a pooled uh, sample, okay, or pooled population. So this is the equation. From this, we calculate the Z score, okay, and or else test statistics, okay, and based on this test statistics, we go and refer to the Z distribution. And based on the Z distribution at that particular Z value, we'll calculate the probability value. And that probability value we called as a P value, which we'll compare with the alpha value, which is your significance level. And based on the comparison, we will take the appropriate decision. If it is less than, then we'll go and reject the null hypothesis. If it is not, then we have to go and go with the null hypothesis. So again, here we will find three different scenarios: lower tail, upper tail, and the two-tailed. Lower tail is something where we uh, assume or we made the hypothesis that the population mean of population 1 is less than the mean of population 2. Okay, so similarly, for upper tail, this would be your alternate hypothesis, and for two tail, this would be your hypothesis. In some of the books, you may also find the hypotheses are being developed in this way or formulated in this way. It's nothing that, okay, this mu2, they have taken it on the left hand side and they have constructed the hypothesis in this way. Okay. So when you are dealing with any particular problem, then you can formulate the hypothesis in whatever way you want, and then you have to go and solve that particular problem accordingly. So if it is a lower tail, then we will consider the left-hand side of the probability. If it is the upper tail, then we consider the right-hand side of the probability. If it is a two tail, then we have to consider the probability on either side of the tails. So this is all the recap. Okay, I'll quickly jump through the problem. Okay, and then we will discuss more, and we will understand through this particular problem. This we have uh, discussed yesterday, and then we'll see that we have seen that how with these two sample tests, we have taken a decision whether we should go with a new formulation of this particular paint, or we should go ahead with the old formulation. So here there is one standard formulation of this particular paint which takes a certain time to dry. Then there is a another formulation with some new drying ingredient which they are claiming that it will reduce the drying time. To take the decision, what they have done is they have taken the two samples. So they have taken the specimens of one standard paint. They have taken 10 specimens of that, and they have also taken the 10 other specimens for this new from this new formulation. So overall, they have 20 specimens, and for each of the specimens, they have collected the drying time, and they have calculated the average drying time for out of those specimens. Similarly, for the other sample, for the other formulation also, they have calculated the mean drying time. So here, if you see the first one looks higher than the other one, but we have to statistically prove that, okay, whether this drying time from the formulation 2 is lesser or higher. Okay, so here if you want to prove that, okay, the mu2 is less than mu1, then your null hypothesis would be mu2 greater than equal to mu1. So this clearly shows that it is a lower tail test. So we will go and calculate the test statistics, okay, by this particular formula. So as I mentioned, no need of by harding this particular formula in Python with just one single line of code with appropriate parameters. You can able to calculate all these test statistics and p-value at one single go. Okay, so this is how I have calculated this z. So this it is z is coming out to be as 2.52. Okay, and which is basically falling on the right hand side of it. Okay, and 1 second. Yeah, sorry, we have to put it, the sequence is wrong. So I have put mu2 first. So this would be mu1 less than equal to mu2. So again, whatever is the sample one, that has to come first, guys. Okay, my mistake, my bad. Okay, so this has to be like this. Okay, so now once you do this, so now it is an upper tail test. Now you found it here that Z0 is coming out to be 2.52. which is falling on the upper tail side. Now you have to go and find out this particular probability. So if this particular probability is less than 0.05, then you will go and reject your null hypothesis, saying that your mu1 is lesser than equal to mu2. So that conclude that your with this probability, as the probability is less than 0.05, you can conclude that your mu1 is mu1 is greater than mu2. Okay, you have rejected your null hypothesis, which states that it is less than equal to mu2. Okay, so like that, you can perform this two sample test by understanding what is your null hypothesis and your alternate hypothesis. So one way is in Python, you can build your own function by knowing this particular formula. You can create your own function and use that function to calculate the test statistics as well as the p-value, or else you have the one single formula. Okay, is it there in this particular slide? Yeah, I'll show you. It's there in the Python notebook. Okay, so we will use the available functions in Python, to perform this particular hypothesis testing rather than going through this custom function. Okay, but if you have to develop any custom function, so you know about how to develop that, you can use this def function, to create your own custom function. Okay, to calculate that. So here for this particular formula, this is your test statistics and this is your p-value. So here the p-value is less than 0.05. So that's the reason I'm rejecting my null hypothesis. I'm accepting my alternate hypothesis. Okay, now let's suppose we are in this particular scenario where we do not have the information about the population variance. In this, again, there are two sub scenarios. One is that we can assume though we do not have the information, but we are assuming they may be equal. Okay. And the second assumption is that they are not equal. Okay. So in those kind of scenarios, in different sub scenarios, we have to use a different formula. So we know that when we do not have any information about the population variances, we have to refer to the t distribution rather than z distribution. Okay, so here for the t-distribution, we need the degrees of freedom. This is the additional parameter which we require, when we are referring to the t-distribution. Here, the t-value for the two sample, here the degrees of freedom would be n1 plus n2 minus 2. So what we are doing is, for one of the sample, what is the degrees of freedom? It is n minus 1. For another sample, it is n2 minus 1. We'll just take the sum of these two degrees of freedom. That would be the degrees of freedom of pool samples, okay, where we are adding the two pools together and then we are calculating the degrees of freedom. So it would be n1 plus n2 minus 2. So that's how the degrees of freedom will be calculated for these two samples. Then we go and calculate the test statistics. So again, you can ignore this. You just take the difference of the two sample means divided by the pool sample standard deviation. So for the pool sample standard deviation, first you need to calculate the pooled variance of the sample by this particular formula. These are plus signs printed incorrectly. So through from the sample, we can calculate the sample variance S1 square and S2 square. So that's simple. Okay, with just one single function, you can able to calculate the variance, okay, from the sample. Those sample variance we will consider, to calculate the pooled variance. Okay, and with this pooled variance, we will go and calculate the standard deviation like this. Okay, which is sp square by n1 plus sp square by n2. So once you just ignore these particular formula, these are complicated. what is the process is, you have to identify what scenario is that, then accordingly you go and calculate the test statistics, and that test statistics you have to refer the distribution, and then you have to calculate the p-value. Okay, so here it is, uh, if the test statistics is negative, then it is more of a lower tail test. Here you have to go and find out the p-value. If the p-value is less than your alpha, then you have to go and reject. Or else you can go with a critical value approach. So I will not discuss because it will confuse you. What you have to do is take the t value, test statistics, calculate the p-value and compare with alpha. So always go with the p-value approach. So if it is on the upper tail, then you again the same thing. If it is a two-tail test, then you have to compare with alpha by 2, or else you have to multiply the probability by 2 and then compare with alpha. Okay, so I'll take the examples rather than going through the formulas. I will explain you through examples that would be easier for you to understand. So for example, now you have these two samples, okay, catalyst 1 and catalyst 2. So the two catalysts are being analyzed to determine how they affect the mean yield of the chemical process. So what is catalyst? Basically, we add catalyst, to expedite the process. Okay. So which one is kind of more effective is something, okay, we have to go and test. So currently the catalyst 1 is in use, uh, but they are looking out for other catalyst, which is acceptable, and they have seen that catalyst 2 is cheaper, and they are thinking that it should be adopted, providing it does not change the process yield. Okay, so if you are getting the same output from catalyst 2 as of catalyst 1 in the lesser price, so then definitely this can be considered, this catalyst 2 can be considered. But before making that change, they want to test it. They want to test it, and they want to run in the pilot plans, and then they want to see whether there is a statistical difference between the mean yields from each of these catalysts. So what they have done is they have taken the catalyst 1 and they have measured the yield of the process, okay, and similarly from the catalyst 2. So now here, the mean of first sample is 92. The mean of other sample is 92.733. And these are the standard deviation from each of the samples. So you have X1 bar, X2 bar, S1 and S2. Now here, uh, the null hypothesis is, here they have taken the two-tail test to compare whether the mean is same or not the same. But certainly, if your interest is to consider that this particular mean is lesser or greater than, then you can go for the low tail test. Here, my objective is to see that both the catalyst is giving me the similar yield. Okay, that is the hypothesis which I want to make. So here the null hypothesis is mu1 is equal to mu2. Always the equal to sign, again one more tip here, always the equal to sign will come in null hypothesis. Equal to sign will never come in the alternate hypothesis. In the alternate hypothesis, we are saying that this mu1 is not equal to mu2. So with this, we know that it is a two-tail test. So this is the first step, you formulate the hypothesis. Second, you go and calculate the test statistics. Okay, by now just think that, okay, you have used the appropriate formula, to calculate the test statistics. Now this is my test statistics. Now I will choose the distribution. So here in this case, I have to go with t distribution because I do not have the information about the population variance. So I'll go with the t distribution. And this test statistics will go and refer to this t distribution, and then I will find out the probability. So as this is a two-tail test, so what I will do is I will multiply this probability by 2. And calculate the p-value. The sixth step is I'll compare this p-value with the alpha value. So if the p-value is less than alpha value, then I will go ahead with the alternate hypothesis. Otherwise, I have to go with the null hypothesis. So here, all that formula has been used and all that calculation has been done. So this is the t-value, okay, test statistics 0.35. And based on this test statistics, you can calculate the probability value. So here it is more of a critical value approach what they have taken. So you can go ahead with the p-value. So at this t-value, you go and calculate the probability, and that probability you multiply by 2 and compare it with this level of significance, which is 0.05. So if it is less, then it says that, okay, here it is less. So we can infer that we do not have a strong evidence to conclude that catalyst 2 result in the mean yield that differs from the mean yield when catalyst 1 is used. So it says that with at 0.05 significance level, you do not have a strong evidence to prove that they are different. Okay, so that means your null hypothesis has been rejected. Okay, and you are going with uh, sorry, here the alternate hypothesis is rejected, and here you are going with a null hypothesis, saying that they do not differ, they are same. Okay. So you can try that. So let's suppose now if you have to do it in Python, just with 3 lines, you can do it. Um, you are going with this. This is one sample. Let's suppose this is catalyst 1. Okay, you have collected all the observations. This is for catalyst 2. You have collected all the observations. From the stats package, you use this particular function t-test underscore ind, means independent. Okay, so here you are passing the two samples A and B. You need not to go and calculate the mean. You need not to go and calculate the standard deviation from these samples. Automatically in the backend, those will be calculated. And here you are mentioning. So if you see here, we are having two different sub scenarios, right? If it is unknown, either we are assuming those population variances are equal, or else we are assuming it as unequal. So that's something you have to pass it here. We are saying equal variance as true. If you make it false, then it will give you a different result because the formula it will use different in the backend to calculate the test statistics. So here you pass this, that's all you have to do. And it will give you the test statistics, which is minus 0.3535. And this is your p-value. So this p-value you can directly compare with the alpha value. Here your p-value is greater than your alpha value. So here alpha value is 0.05, right? So this value is greater than 0.05. So if it is greater, then we have to go with the null hypothesis. And what is our null hypothesis? Null hypothesis says that these two yield of the population, mean yield of the population is equal. So that means the yield coming out from catalyst 1 and catalyst 2 on an average, they are equal. So now you can take a decision. Now you are getting the same yield from catalyst 2 as you were getting from catalyst 1 in a cheaper price. Now you can go and replace catalyst 1 by catalyst 2. Okay. So that's how this particular problem has been solved. So I'll take a pause. Let me know if this example is clear to every one of you. Just understand this particular slide. Okay, you have two samples, and now if you have two samples, then it becomes a two sample test. Now you have to go and perform the two sample test. In the two sample test, you have to understand whether the population variances are given or not. Here in this case, nothing is given. We just have two samples. So I will go ahead with the second scenario where population variances are not given, are unknown to us. If it is unknown, then we have two assumptions what we make. First assumption is we generally consider that those two populations are kind of very much same, okay, and they would have the same equal variance. So in that case, we go ahead and mark this equal variance equal to true, and then we perform this test. So if you see that we are just using one single line, to perform this hypothesis test and passing these two samples to that. And based on the p-value, we have to go and take the decision whether we should accept the null hypothesis or reject the null hypothesis. Okay, so you can stop me anywhere, if you have any questions. Okay, so if no questions, then let's go and talk about another scenario. So now this scenario is simple. Okay, so we have seen how to solve this. Now we'll go ahead with this. Now, when we use this particular scenario, when we say that the population variances cannot be equal. So for example, now you're using, so here in this case, the process is the same, right? Catalyst 1 and catalyst 2 are being used for the same process. So that's the reason there is nothing wrong in assuming that okay, the variance could be the same, okay, in both the population. But if it is a different process altogether, okay, then in that case, we can assume those are unequal. So if we are assuming the population variances are not same, then the formula would change. So here it is much more complex formula. Okay, so it's there in the handouts. Okay, you can go and refer to if you want to understand the formula. By now, I'm just ignoring and directly jumping into the example. So here, there is a two different regions, different city, different, I would say, counties. Okay, one is like Phoenix, and the second is the Arizona. So in this, each of these counties, there are multiple uh, communities are there. Okay, multiple communities are there, and for each of the communities, certain measure has been calculated. So, for example, in this case, they have taken the arsenic concentration in the drinking water supplies. So, in this particular county, they went to this particular community, Phoenix. They have measured the arsenic concentration in the drinking water. Similarly, for all these 10 different metropolitans or communities, okay, they have measured the arsenic concentration. Similarly here, okay. Now, these are the two different samples coming out from two different population. Here, the regions we have to consider as a different, right? Here, nobody explicitly mentioned that, okay, whether the population variances you have to assume as equal or unequal. So based on the domain understanding, based on uh, your understanding about the population, you have to decide whether you have to consider both the variance as equal or unequal. So as these two are different regions altogether, so I cannot assume that whatever process they might have used, for the public drinking water could be the same. So in that case, I will assume that the population variances in these two population would be different. Okay, would be unequal. So now exactly the same kind of an exam problem as we have seen before that was related to catalyst. But the only thing changes here is here we are assuming the variances of the populations are unequal. Okay, there we have assumed it as equal. Rest everything is the same. So if you look at that Python code, just the only one parameter we have to change, like that equal sign equal to true, we have to mark it as false. Variance equal to true, we have to mark it as variance equal to false. That's all. So here first we have to go and uh, frame the hypothesis. Here we are saying that arsenic concentration in both the regions are equal. That is my null hypothesis. And alternate would be different, opposite, which is like the arsenic concentration, average arsenic concentration, both the populations are not equal. That is my alternate hypothesis. So the approach is the same. You go and calculate the test statistics, and then the test statistics at a particular degrees of freedom, you have to go and refer to the t distribution. And with that t distribution, you have to calculate the p-value, and that p-value you have to compare with the alpha value. And based on the alpha value, you have to take the decision. It's as simple as that. Okay. So here, you need not to go through all that steps. You directly go here. Okay. Here, just you pass these two samples and say equal variance equal to false. That's all. So this is my test statistics. This is my p-value. Just by running this particular line of code, whatever p-value comes out, you just that particular p-value you have to compare with the alpha value. Here the alpha value is equal to 0.05. So here it is p-value is less than alpha. So in that case, we have to go with the alternate hypothesis. I can go and reject the null hypothesis. Okay. So why I'm explaining all these things, all these tests. See, there is a slight difference, okay? But you can go and try this at your end. You just take this particular samples and just see that what you are getting when you are saying equal variance equal to false and equal variance equal to true. You will get significant difference in the p-value. So that's how it is very important first you to define the problem. I've been telling you guys that first the major task is to understand the problem. Rest everything I by practice you will get it. Okay, it's just a step-by-step process. Okay, you need to know what function you have to use, what arguments you have to use, how you have to pass the parameters or values to those arguments. If you understand that, it's a seamless process. But if you go wrong at the first steps in defining the problem statement, instead of false, if you define it as true, then the entire decision will go wrong. And the second thing, you need to understand that what are the different ways by which you can perform these tests. Okay, so these are all different ways. Now once you understand the problem, you have to see that where exactly that problem will fall in this, or in this, or in this. So that classification, that translation of the problem statement into analytical problem is very, very important. Once it is done, then you have to use the appropriate technique to solve that particular problem. Now you would be seeing that so many variances, so many scenarios. Is it important to remember? Why is it important to remember? It's important because, see, if you do not use the right approach, to solve a particular problem, you may end up in taking the wrong decision. So that's the reason you should be aware of all those things. Until unless you are not aware of these two sub scenarios, you may proceed with one single approach and you may end up, taking the wrong decision. So from the statistical point of view, you should be aware like what all different tests could be possible and which kind of test would be suitable for your business problem, and then accordingly you have to go with that particular approach. Okay, now in this two sample test, there is one different kind of scenario which you may come across. Now we talked about all the independent samples. Now there could be a dependent samples. Now what could be the case of dependent samples? Now and this is again most widely used, to solve a problem statement. For example, now you have to test whether a particular drug is working or not. Okay. What you will do, you will take one sample. Uh, Before giving the drug, okay, before giving the drug, you will, let's suppose you will measure a particular parameter, for example, weight of that person. Okay. Now let's suppose in your sample, there are 10 people. There are 10 people. Okay. And you have collected the weights of all the 10 people before giving the drug. Now, let's suppose you give the drug to that particular person and continuously for a month. Okay, it's a weight loss kind of a drug. And after a month, you will again collect the weights of the same sample, of the same people. You will not go and measure the weights of other people, right? You will take the same samples. Here, the sample is one only, but here the values which are coming out of the sample, you can consider as a two different samples. Okay. Here the object in the samples are the same, but you are creating two different samples from the same objects. Okay. Now, after the drug is given, okay, you have collected the same weights. Now, for example, just think about the weight loss program or diabetes control program or something like that. Okay, and you want to see what is the effectiveness of that particular program. Is this something after giving that particular drug for a month, whether the weights are gradually reduced for all those subjects, okay, which are included in that particular sample. So now this is known as dependent sample. Here we do not have two different samples. Here we have only one sample. On that only we are doing the experiment, and we are generating two sample, one sample before the experiment, another sample after the experiment. Okay. So these are known as paired or matched samples. Okay. So here what we will do is, so this is, let's suppose after the experiment, now you have these two columns. Okay, so before experiment weights and after experiment weights. Now we will go and find out the difference between the weight between these two. Okay, that is uh, BW minus AW. So that would be your DI. So before the experiment, let's suppose the weight is 100 and after that it is 80, then 100 minus 80, 20 would be the difference. So for that, I will collect for all the 20 observations, 20 objects which I have in my sample. So that is known as DI. Okay. So here, now I will calculate this DI. Okay. Okay. And then I will take the mean of this DI. Now that would be my D bar. Okay. Now, whatever difference, okay, if you're claiming that your weights will come down by 20 kgs or 5 kgs or whatever, that will become my D0. Okay, whatever I'm claiming. Now, that difference which is coming out from the sample, I'll compare with that particular claim of difference. If somebody is saying that if you take this particular drug, your diabetes, you know, value may get down by 10 or 20, whatever unit it is measured. Or if the weights, then if it is reduced by 5 kgs or 20 kgs, whatever it is, that's something I'll compare with this mean difference. Okay. And I will calculate the standard deviation of that particular difference column. So I'll calculate the mean and I will also calculate the standard deviation. So that would be my SD. And this SD by square root of n is known as standard error. We discussed about this, right? Standard deviation divided by square root of sample size is nothing but your standard error. So this would be the formula for T, which is test statistics. And after that, you know what to do. So after that test statistics, you go and find out the probability, and based on the probability, you will take the decision. Okay, whether to accept your null hypothesis or reject your null hypothesis. Now, again, firstly, what you have to do is whenever you are dealing with any problem, first understand whether those samples are dependent samples or independent samples. If they are dependent sample, then go ahead with this. We also called as this particular test is also called as pair t-test. Okay, so pair t-test means there is only one set of samples on which only we are creating two different samples. Okay, before the experiment and after the experiment. So now based on that, you can formulate the hypothesis. In all these tests, there are only three possibilities of hypothesis. Either it could be a lower tail, or it could be an upper tail, or it could be a two tail. So let's go and look at this example. So these are all real examples, guys. That's the reason you are seeing a little bit more complicated and more business specific. So that you can relate how these tests are being used in different domains. So, for example, in this particular article, they're comparing methods for predicting the strength of these steel plates. Okay, so there are two different methods by which they are comparing the strength of this. So data for these two of these methods. So there are two procedures. So this is I'll call it as a K procedure and L procedure. So it's difficult to pronounce. It's Carlway and Lay procedures. K procedure and the L procedure. These are the two procedures which they are using, to measure the strength. Now what they are doing is, now here they can't use the two different samples and measure and consider these two different procedures, right? It does not make sense. So they are taking one sample only and they are using these two different methods on top of it. So here the sample is one. So that's the reason it is called as dependent sample. Here the sample is one, but the procedures are different. So now they have used this particular two different methods and they have measured the strengths of whatever number of steel plates are available in this sample. Let's suppose 10. Then they have taken these 10 and they have measured these strength of these steel by using these two different procedures. Now they want to see whether there is a difference in the average strength or there is not. Okay. So these are those. So from the first, this is the first guider, okay, or the steel plate. From this particular K method, the strength is 1.1. For from this method, it is coming out to be as 1.06 form. So here, this sample is standard. Okay, these are the fixed 10, 9 or 10, guiders which they have selected. And on top of that, they have used these two different procedures. Okay. Now they have taken whether there is a difference between the strength which has been measured by these two different procedures. They have measured by calculating the difference as DI or DJ. Okay, that is the difference. So there is a difference, there is a difference. Okay. Now we have to go and test it. Is there is a significant difference? Okay, in these two values. So here my H naught is, I'm saying the null hypothesis, there is no difference. Okay, so here I would say that mu D, which in bracket, which is nothing but mu1 minus mu2, it is equal to 0. I'm saying that there is no difference. And alternate hypothesis says that there is a difference, which is mu D is not equal to 0. So here the population data is not there. So for that, we are going and using this D bar, okay, which is this sample difference mean, okay. So this I will use it and I will consider that, for calculating the test statistics, how can we get this D bar and SD, okay, from the sample. So for that, you need to kind of calculate this difference column. And then based on this difference column, you calculate the D bar and SD. So you have this information, what is the sample size. Now, based on this, you go and calculate the probability from this T distribution. And then based on that, here in T distribution, the degrees of freedom would be n minus 1 because here there is only one single sample, it is n minus 1. So at that particular degrees of freedom, you go and calculate the probability and that p value you compare with your alpha, and based on that you can take the decision. Okay, so here the p value is coming out to be as 0.0002, which is less than 0.05. So in that case I can go and reject my null hypothesis. So we can conclude that strength prediction method yield different results. Now this is important. So now practically see that, what exactly can be inferred out of this. So for example, in one of the plant, people are using this K method and another plant, they are using L method, to measure the strength of the steel placed. Then that means they are not following the standard process. And for that, let's suppose I ran this particular experiment. I took one set of steel plates, and I've used these two different procedures to calculate the strength, and then I've statistically proved that these two procedures are different. Now the management or the business has to standardize the process, and all throughout the plant they have to follow the same procedure to measure the strength of the steel. Okay, so this is what we understand from this particular problem. Now, see how easy it is, to do it in Python. So in Python, let's suppose you have these two observations. Here you just say t test underscore rel. Rel means relative. Okay, so this is the function which you have to use for performing the pair t test. And you pass these two. That's all. You need not to pass anything because there is no any other assumption you are making here. So you just pass these two samples to this function, you will get the p-value. And once you get the p-value, you can take the decision. Okay. So this is about two sample mean test. Now we will get into two sample proportion test. Now, again, the whole intuition is the same. Here, instead of mean, we'll go with proportion. And with the proportion, the good part is that, okay, every time, we have to go and infer to with the Z distribution only. We need not, there is no confusion of choosing the Z distribution or T distribution. Every time, wherever the proportion comes, we'll go with the Z distribution. Here also, there is certain formula, which we need to understand when it comes to calculating the standard deviation or the pool standard deviation, all those things, and to calculate the test statistics. Okay. Now, this is the standard deviation. Yeah. This is the formula, for the test statistics. Here, as I mentioned, for proportion, we always use Z distribution. So here we are using Z score. Okay, so now let's understand this particular problem. Second. Yeah, this is a problem. Okay, so here again a very interesting use case, and this all these use cases, if you see, these are being published in particular kind of journals. Okay, and lot of such research people do to publish lot of such research work to the people to understand how the things are in the world. Okay, so for example this, so in this particular issue of journal, so they kind of they measured a certain kind of medicine or diagnosis, whether it is effective or not. Okay, they have made the study on that. So for that, what they have done is they have compared the efficacy of this particular kind of medication, which is given by this particular gentleman, with a placebo. Let's understand what placebo is first. Okay. Uh, you guys, have you ever, anybody has used homeopathy medicine, guys? Anybody? So if you take homeopathy medicine, every time or whatever medicine you get, it looks the same. Okay, it looks like a sweet pills. Okay, so it's some of the people they say that these homeopathy medicine, this is nothing but a placebo. Placebo is the, you can think about that. If you come to me, let's suppose I am a practitioner. If you come to me with a particular problem, I'll say that I will not have any medicine. Okay, I'll just take some chocolate. I'll say that I've mixed something in this which will, recover you. And I have done all the things, whatever possible. I've, got all the things which is required, to cure you, that I've mixed in this particular chocolate, and you take it. When you have it, you will not identify, is there any ingredient or not. But that psychologically, you will think that, okay, it will work. Okay. And with that, mindset, if you take that particular medicine, you will feel that okay, something is happening and you are recovering, right? So that is known as placebo effect. Okay. Homeopathy medicine is also like that. So you go with any problem, whatever medicine you'll get, it will taste the same. Okay. And people say that it's just like psychologically you think that this medicine would work, and it eventually it will work. So now they want to compare this particular medicine, which is given by this particular gentleman. They want to prove whether it is effective or not. So what they have done is they have taken the two samples, two set of people, okay, with the same kind of problem. And what they have done is to one patient, they have given the placebos, like they have just given the sweet pills. And the second person, set of people, they have given this extract, okay, which has been discovered by this particular person. Uh, and then they have seen what is the effect. Okay, if the effect is kind of same, that means that medicine is nothing but equivalent to a placebo. Okay, and that medicine is not scientifically effective. Okay, we can infer based on that experiment. So what they have done is they have randomly assigned the two groups. Patients were randomly assigned in two groups. One group received this particular person's wort, St. John's wort. This is the medicine name, and the other person received the placebo. After 8 weeks of that medication, 19 of the placebo treated patients showed improvement, whereas the 27 of those treated with St. John wort, they were showing some improvement. Okay. So 100 patients each has given these two different medicines, and they have been evaluated after 8 weeks. And this is the result. 19 of the placebo treated patients, they showed improvement, and 27 of those treated by this medicine, they have shown improvement. So if we compare the number, it looks higher, but we go and scientifically and statistically we'll go and prove that whether it is greater or not. So now there is a question: is there any reason to believe that this particular is medicine is effective in treating the depression problem? Okay, and they have mentioned, okay, use this zero point zero 0.05 as your significance level. Now I'll go and so it is a proportion. It is I want to compare the proportion. How many number of patients? What is the proportion of the patients who have shown improvement by using this placebo treatment, and comparing with the proportion of the people who have shown improvement by taking this particular wart treatment. Okay, and then I will compare. So it's all about proportion. So here the P1 hat is 27 by 100 and P2 hat is 19 by 100. So these are the two proportions. Okay, and I have all the information N1, N2, sample size, and this is the formula, okay, which I have to use. So first I have to go and find out the pooled proportion. So pooled proportion would be uh, x1 plus x2 by n1 plus n2. So 19. So the number of people who have shown improvement in each of the sample, that I will add it divided by the total sample size. So that is my pooled proportion. And with this pooled proportion, I will go and calculate the standard error. And this is the difference between the sample proportion, P1 hat and minus P2 hat. So this is how I will substitute the values into this particular formula and calculate the Z score. And based on this Z score, I'll calculate the probability, and based on the probability, I will take the decision. If the p value is less than 0.05, I'll go and reject the null hypothesis. So it seems that the p value is coming out to be as 0.177, which is greater than alpha. So in this case, I will fail to reject the null hypothesis. Okay, I have to go ahead with the null hypothesis only. And what null hypothesis states that what is the null hypothesis? Here says that proportions are equal. Okay, so though we are seeing the number is high for what, but statistically we couldn't able to prove that, okay, they are different. Okay, so we have to say that we cannot reject the null hypothesis. So there is insufficient evidence to support that the claim that St. John's wort is effective in treating the major differences. There is no evidence to prove that. So in that case, we are saying that they are not same, they are different. Okay. So they are different means, yes, so in their different means, definitely the what could be effective than the placebo. Now I can go and perform the upper tail test to further prove that, okay, yes, this is effective. More number of patients by consuming this particular medicine, they are showing improvement. That's something I can do. So here it was just whether they are same or not the same. That's something what we have solved in this particular problem. So when it comes to Python, either as I mentioned, you can go and create your own custom function, or else you can directly consume the functions which are available. So here you just pass the proportion, so 27.27.91, and you pass the sample size. That's all. So you will directly get the p-value, and based on this p-value, you can take the decision. So just with one single line, you can able to solve the problem in Python. So that's all, guys. So these are all major hypothesis. Okay, so we discussed about one sample test. We discussed about two sample test, and that too for mean, for proportion. Now you would be thinking about what about more than two samples? So in the next class, we will talk about there are only two tests, guys. One test, for mean, one test for proportion for more than two samples. For more than two sample mean test, we do ANOVA test. You might have heard about ANOVA. It is analysis of variance test. And for more than two sample proportion test, we go with the chi-square test. So those are the two tests which we'll discuss. And with that, we are done with this hypothesis testing. So I'll take a pause. Let me know anybody has any question. So guys, it may sound confusing, it may sound complicated, but if you sit and solve the problems, okay, for each of those scenarios, it will not look complicated for you. And if you do it in Python, it's very, very easy. Okay, as you have seen that with one single line, you can solve these hypothesis testing problems. All right, so I will stop here. Let me know anybody has any question, any comments, anything you want to discuss. Okay, so if there are no questions, then we'll up. So we'll connect tomorrow. Thank you guys. Have a nice day. Take care.